All right. So yesterday we started a PID controller example, and basically PID is just combining the steps of designing a PD and PI controller based off of second order approximation. And the PID controller just contains the PD component, which is a zero added zero, and a PI component, which is a added zero and a pole at the origin. And um, To do the design, we designed the PD controller first to shape the root locus into something that we like. And then we use our PI design to preserve the shape of the root locus because now we no longer need to change the root locus shape. We just want to reduce steady state error. And so the PD controller design is probably the hardest part. Once you get the PD controller done, you can just design the PI and you're done. So we started an example on PID controller, we're trying to get 2/3 peak time. So we're trying to reduce the peak time of the uncompensated system by 2/3, while maintaining 20% overshoot with zero steady state error. And we get our performance metrics by looking at the uncompensated system with 20% overshoot. And then we found the uncompensated closed loop poles using MATLAB. And then once we got that, we were able to come calculate the uncompensated peak time using second order approximation. Uh, if yeah, so then once we get that, we get the desired peak time of the compensated system, and then using the desired peak time of the compensated system, we're able to work backwards and determine the corresponding natural frequency of the compensated system that we want. And then once we get that, we can then determine the location of the compensated closed loop poles, which is defined right here. Then I was able to find that, and we got a pole location of -8 plus or minus 15.8. Now, we did all of that and we haven't started the PD controller design, but now that we are we have the desired closed loop poles, we just need to move the root locus such that it passes through that point, and we do achieve that using a PD controller. So that's what we did yesterday. And then I'm just look at my notes. Okay, so we now have our desired closed loop pole location, and then I'm going to visually draw out the pole zero map. And we have, let's see, imaginary axis, the real axis, and then we have a pole at -3, -6. Let me draw this a little bit more spaced apart. -3, -6, uh, a 0 at -8, and a pole at -10. So it's a little cramped here. So let me just maybe I'll put a 0 to the left of all of this, just to give myself more space. Yeah, I'll put my PD 0, let me put right here. I'm gonna call it -ZC. Should be ZCD. And then my evaluated point is going to be at -8.13 plus 15.8J, probably a little higher up. This is -8.13 plus 15.8J. And then I'm going to draw all the phasors from each pole in 0 going to that point. And I'm going to define it as theta 1 for the first pole, theta 2 for the second pole, theta 3 for the third pole, phi 1 for the first 0, and phi 2 for the second 0. And what we're trying to find is we're trying to find phi 2 now. So maybe here we're going to write find phi 2 to find minus zc, or the value of zc. So we're going to use the angle criterion, where it's going to be 2i plus 1 multiplied by 180 degrees is equal to your sum of your angles of your zeros minus sum of the angle of your poles. And that's going to be equal to phi 1 plus phi 2 minus theta 1 plus theta 2 plus theta 3. Okay, so we can determine everything except phi 2 using trig. Theta 1 is equal to arctan of our evaluated point, which is going to be 15.8 minus the height, which is 0, and then minus 8.13 minus 3, so that's plus 3. That's going to be equal to, if I plug this into my calculator, I get 15.8 divided by negative 5.8, or the negative 5.13, and that's going to give me a negative angle. But if we look here, this is a quadrant 2 angle, because we're having a positive height but a negative x component. And this angle here that we're given is a quadrant 4 angle, so we just add 180 degrees and we get 108 degrees. Okay, so theta 2 is arctan of 15.8 divided by negative 8.13 minus 6, so that's plus 6. And same deal, we get a negative angle, but we're aiming for quadrant 2 because of the positive y component but negative x component. So we add 180 degrees, and that gets us to 97.7 degrees. All right, theta 3, we get arctan of 15.8 divided by negative 8.13 minus 10, so that's plus 10, and we get a positive angle of 83.3 degrees. And phi 1, we get arctan of 15.8 divided by minus 8.13 plus 8, and we get 90.5 degrees. So these are all the angles, and then I plug this into the equation where I get 2i plus 1 multiplied by 180 degrees is equal to 90.5 degrees plus phi 2 minus 108 plus 97.7 plus 83.3 degrees. So then I'll write it out. I get 2i plus 1 times 180 degrees is equal to phi2 minus 198.5 degrees. And with my thought process here, I'm aiming for an angle that's between quadrant 1 and quadrant 2 because our reference point is above the real axis. So meaning that we can only have a positive or negative x component, which bounds our angle to be in quadrant 1 or 2. So we want to aim for a Q1 or Q2 angle. Likewise, if I had this point below the real axis, then we're aiming for a Q3 or a Q4 angle. So for Q1 angle or Q2 angle, if we set 180 degrees equal to minus 180, so if I was equal to minus 1, then we get this. This is for I is equal to minus 1. So then we get phi2 is equal to 18.5 degrees. Sorry, I'm like making things a little bit compact here because I really don't want to create another page just for finding the zero location. Any questions on the angles and why I chose a quadrant 1 or quadrant 2 angle? Hope that makes sense. Yeah. Possible that Z could be on the right side of the real axis, but it has to be on the positive part of your why quadrant 1? Yeah, you know what? I'll just make a new page. I think it'll be good. Good visual. I think this is a really I don't think the textbook talks about it too much. It kind of just implies it, but it's always been a confusion every year when I go over this. Uh and let's clean this up. I'm just going to remove these lines here. So we're only looking at that point here. So it's a lot less confusing. So this angle here, if I actually drew it true to its scale, we can see that phi2 is going to be less than 90 degrees, right? If I drew, let's say, another zero right here, maybe I will call this minus ZCD2. And I drew this line here. I call this phi3. Phi3 is, I guess, this is not the correct notation, but it's in quadrant 3 or quadrant 2 now, because the angle, actually a better notation would be it's between 90 to 180 degrees. While phi2 here is between 0 to 90 degrees. If I push the ZC all the way to negative infinity, it would actually converge to 0 degrees. If I push this right under, as long as it's to the left of this, we know it's quadrant. This is Q1 and this is Q2. And if I increase the ZC all the way to positive infinity, the maximum value I get out of that angle is 180 degrees. So because of that, I'm bounded between these two quadrants. So we only choose angles between those two quadrants. So if I do flip it, now if I flip it to the where instead we have down here, then it's the opposite. We're now bounded between Q3 and Q4. The only possible angles are between Q3 and Q4. So we are now bound to Q3. I guess phi2, phi3 are bounded between, I guess, Q2 or 180 degrees to 360 degrees. So that's between Q2 and Q3 or Q3 and Q4. And you don't have to use 180 and 360. If I use Another way of saying is I can bound it between 0 degrees and minus to minus 180 degrees. So if I go from 0 to minus 180, I'm just going clockwise. Likewise, I mean, this would be a trip, but if I were to, I could say I'm bounding it from minus 270 degrees to 0 degrees as well. That's the same because we're just now reversing the direction of how we reference the angles, but maybe we'll just stick with one direction and I'm not going to give you that choice. Stick with positive angles. So then you just won't mess up. If you feel very confident, you can go with negative angles, but make sure that the negative angle still ends up in the right quadrant. But I like to just stick with one, just so you just don't confuse yourself. When I stick with all positive angles, it's fine. I can just always subtract 360 if the angles are huge. Okay. So now I'm going to find does that answer your question? All right. Okay, so I'm going to find the location of 0, and the equation is just basically saying that tan maybe I'll follow the format of how we find the angles. When we find the angles, we say phi2 is equal to arctan of your reference point subtracted by the actual location. So then we do minus ZC. That's how I write it. So basically it's the same as saying tan, but we don't know what now we know what phi2 is. We don't know what ZC is. We rewrite it as tan of phi2 is equal to 15.8 divided by negative 8.13 plus ZC. And when I solve for ZC, I get 55.4. Remember, if you're doing this on your calculators, especially on the exam, set your calculators to degrees, or if you want to do this in radians, set it to radians. Typically, I find it, well, I'm very used to doing this in degrees, so set your calculator to degrees, please, on the exam. And in MATLAB, use tan D, or MATLAB, you want to use tan D for degrees. MATLAB. I think it's the same in Python as well when you use their trig. All right. So I'm not going to include the PI controller part of this because all we have to do now is just add a pole at the origin and a 0 close to that pole. So that we can just do directly on the computer. But we're pretty much done. So PID controller is just mainly designing the PD controller part and then just adding the PI component next. So our controller is going to be CPD of S is equal to K PD multiplied by S plus 55.4. Man, maybe I should just, you know what, I'll just embrace the new page. It's all electronic anyway. Well. Okay, CPD is going to be that. So now we need to figure out the corresponding gain. Well, all right. I'm going to talk about, I guess, why it might be okay to just find the gain right now before adding the PI component, and then I'll talk about about finding the gain after adding the PI component, and we can look at the differences. It's not really in the notes, but I think there's a little bit of nuance. So let's just go to MATLAB right now. So, and to write it down so you can have it fresh in your head, G of S is equal to S plus 8 divided by S plus 3 times S plus 6 times s plus 10. So that's our original uncompensated transfer function. We're aiming for percent overshoot of 20%. And we want our TP compensated to be 2/3 of the TP uncompensated. So those are our design parameters. So we're now going to choose, and we want our closed loop pole to be at -8.13 plus or minus 15.8 J. So we want the compensated pole now to go through there. So we need to find the corresponding K PD. So if we were to do that by hand, KPD would just be equal to 1 over magnitude of CPD of S times G of S, evaluated at S is equal to -8.13 plus 15.8 J. So if we do that by hand, it would look like that. I'm going to just skip that and just do it on MATLAB. Okay. Let me let y'all finish copying that. We're actually way ahead of schedule. I'm a little bit worried about like not having anything to talk about week 11, but maybe we can just hang out. No, I'll if we finish everything early, what I'll do is I'll probably just do some quote unquote fun lectures on controls that won't be on the exam, but just more like how these things are applied in different areas. Maybe I can do a little bit about different aspects of controls. Maybe like a very, very short introduction to different like classes that are taught here. I can give you like a preview of what those classes are about too. Maybe we can do that. Mainly it's just because we're almost done with we're done with chapter 9 very soon because we have lag lead coming up next, and it's the same exact example, but just combining lead and lag. And then once we're done with that, we're on to chapter 10. Chapter 10 is going to be a long one, similar length as chapter 9, but I think we would finish that in 2 weeks anyway. So, yeah, we're actually good on time. It's because I caught out chapter 6. Yeah, yeah. And also like please like if this is probably the meat of this class, chapter 9 and chapter 10. Chapter 10, I think, is a little bit more important than chapter 9 if you do research, but chapter 9 is important for industry, if I had to guess. So that's why I think it's good to take it slow on these chapters. Anyway, yeah. Calculated by hand. I remember you did this example with like 2 classes or a class ago. Yeah. I'm just wondering that would you expect the gain for the PD controller here to be very small or very like so low, like less than 1 or above 1? Because I remember it's going to be more than 1. Yeah. For S, you have 1 over like I guess you plug in the complex conjugate for X, right? Yeah, and I want to do this by hand next because I'm going to tell you why it might be good enough to just find the gain for the PD controller and not the gain for the integral controller. And I want to show you by hand as well. But maybe for now, what I'll do is I'll just write it out. I don't have my calculator on me. I don't have the values out, but the way it's going to look like it's going to be this inverted. It's going to be these two inversed. So we get the absolute value of s plus 3, s plus 6, s plus 10 divided by s plus 8 times s plus 55.4 and evaluated at this point. So then if I work out long division, or not long division, but I need a lot of space, I plug in S and I get minus 8.13. And I'm going to separate the real and imaginary components here. So minus 8.13 plus 3 plus 15.8J times minus 8.13 plus 6 plus 15.8J, and then minus 8.13 plus 10 plus 15.8J. Oh, okay, yeah. Okay, cool. So then same thing in the denominator.
The reason I asked the question is because I saw that you inverted it last class, and I was wondering why you do.
Oh, why we do the inversion? Yeah, it's because, yeah. Okay, so it's because we want 1 plus kgh is equal to 0. That's the definition of poles. This is the definition of a pole. It comes from the closed loop transfer function, which is kg over 1 plus kgh. Where if 1 plus kgh is equal to 0, then that's the definition of a pole. So then if this is the definition of a pole, then if we take the magnitude of this, we're saying kgh is equal to minus 1, and this is where we get our angle criteria, that kgh is equal to 180 degrees. And then if we divide both sides, we get k is equal to minus 1 over gh. But this is a magnitude, so it's going to be, that's where we get it. Yeah. Yeah, no problem. All right, so share my screen. All right, so this is my PID example, and step one is to define our open loop transfer function right here, and then we get our root locus, and then we are looking for zeta is equal to 0.456, which corresponds to 20% overshoot. All right, and you have to trust me that the gain is at 122, but if I were to look for it, click it right there. Close enough. 122, right there. 0.452. So that's where I get my gain. And then what I do here is I put it into the closed loop transfer function form with kg, and then I do step. And our original calculation says that our peak time we calculated it to be 0.296 seconds. So let's see if second order approximation is correct. That's our peak response. We said it was 0.298 or 0.296. It's actually 0.298. Makes sense because the third pole is decaying fast, but not too fast. So it's making the overshoot or the peak time a little slower. That's fine. And then we added our pole, which is at, I think it was 50. Did I write 55.4? It shows 55.9. All right, 55.4. And then now what we're going to do is we're going to do the new open loop transfer function, which is D times, I think I use C times G. And here we get that. So now you can see our root locus looks a lot more different from our original one. The shape has changed quite a bit. And then we're seeing now if our root locus passes through negative 8.13 plus 15, which is going to be roughly there. Yeah, see, so we got it. So negative 8.14 plus 15.8 I, which has a gain of 5.35. Now, if you look closely, we do have a third pole right there. It's really close. Oh no. It's really close to that. Oh well, so 5.35 is the gain we got. So we found that KD is equal to 5.3. So now we do KD multiplied by our PD controller multiplied by open loop transfer function. And you can just ignore this. So this is just putting the gain in the in the feedback, because if I were to look at MATLAB's definition of feedback, the way they draw it is they have M2 pop up as the feedback. Don't worry about it. Or just look at GCLPD. So now we have the new compensated system, and now we can see that we now have a peak time of, we're aiming for 0.2, which is roughly where we're at. We now have a peak time of 0.18. So that's roughly 2/3 reduction. Now, what I did here though was that this is the orange line is the original response, but I just normalized it. So that way we can see if we were to do apples to apples comparison, it would look more alike. This is just the PD step performance. Blue is the way the textbook defines PD controller. MATLAB has a slightly different way of putting the K gain for the PD compensator, so I wouldn't worry a bit too much about it. Okay, so then the final step is to add a integrator, and we're just going to add one. So I added one at 0.5, but let's start with 0.1 first, because I wanted to show you what happens when we put a zero really close to the origin. So we're just adding the Poland zero close to the origin. And here we're still going to use K is equal to 5.3 instead. So now we are adding a PID compensator. And if you actually look here, this is the PI compensator, and we compare it to that. Well, click there. Yeah, they look very similar. Similar in shape. The grid's kind of messed up. That's okay. So if I choose that, look at that point again, we're not going to have it exactly negative 8.13 plus 15.8. It's kind of like negative 8.08 now plus 15.8. But since this design is using second order approximation, all of this is approximation. It doesn't really matter. We're close enough to our desired poles. So the gain is still 5.34. It was like 5.35, now it's 5.34. I'm just using 5.3. And then now we're going to simulate it, and I'm going to show you the PID, the PD, and the uncompensated system. And that's because I changed a stick with book notation. All right. Now, I need to increase the scale. So we're going to go to 50 seconds, and the resolution doesn't look great. So I'm going to increase it to maybe 50 points. And let's run this again. All right. Now you can see here, we have this very, very slow convergence to the final value of 1. And you can see that what the PI does is it reduces the steady state error to 0 because we're increasing the system type by 1. So this is a type 0 system. And you can see here the PD does reduce the steady state error compared to the uncompensated system, but doesn't make it 0. Now the PI controller has a slow convergence to 1. And the reason why the convergence is so slow is because of this pole we added at the origin. If I zoom in really, really closely here, you can actually see that we actually have a closed loop pole really close to the origin, meaning that this decay here is really slow. We have a very slow decay. So if we ignore this peak response here, this response actually looks more like a first order response if we were to ignore this oscillating part. Uh, Now, if I were to zoom into this section here, you can see that my peak times for the PID and the PD are very similar um, compared to the uncompensated system. The PID system might actually have a slightly slow. Oh, actually, they are identical. All right. Well, never mind. We're good. It looks very jaggedy. I wonder why. All right. So now, if I want that really slow transient response time to move a little faster, I can move my pole location or I can move my zero to be further away from the origin. So I'm going to choose zero point 0.5 now. And if I were to run it again, and so now you can see this convergence is a lot faster. So it converges at 5 seconds compared to, I think it was like 20 seconds earlier. Um, Peak time is still similar, and now we're just converging a lot faster. So if you put your zero arbitrarily close, like if I put 0.001, then it's going to converge really slowly. Yeah, so you see now it's converging really slow. Even 50 seconds isn't long enough. So I usually choose zero point 0.5 or 0.3. It doesn't matter too much. All right. Now, if I put a zero further away from the origin, then my root locus shape will change more. So if I now look at um, my gain, I want it to be at 8.13. You can see that my real I went from 15.8 to 16.5, and I have to use a higher gain of 5.9 now. So just some consideration. You can still use a gain of 5.35 though, and I'll talk about that now. Okay, so this is the C. This is our gain for KPD, and now if we were to calculate the gain of KPID, which is equal to 1 over CPD, or maybe I'll do CPI times CPD times G. And what I'm going to do is I am going to break CPI separately. And then we get um, CPD times G. And based off of the definition above right here, highlighted here, this is the same as this. KPD divided by CPI. We good so far? All right, good. So then what I'm going to do is I'm going to just multiply this by KPD, and then I'm going to write out CPI. And that's going to be the absolute value of our pole at the origin divided by the absolute value of our zero. And let's say we choose a very small value of S plus, let's say 0.1. And we evaluate it at Yeah, let's do -8 plus 15.8j. Let's do that point. Then we get this KPD divided by the absolute value of -8 plus 15.8j, and then minus 7.9 plus 15.8j. And this value here is roughly equal to 1. Because the pole and zero are so close to each other, and we're evaluating to a point relatively far away, their magnitude lines are roughly the same. In reality, this would actually be the actual reality is that this value here is slightly greater than 1, but we can just say it's roughly equal to 1. And that's why we can still use this approximation. Any questions? The only time we can't use this approximation is if we're taking a evaluated point that's kind of close to the pole and zero at the origin. If that's the case, then we need to find the new gain. But if you use but in our homework on the exams, actually, I take it back on the exams, but on the homework, if you use KPD as your final gain instead of KPID and find a new PID gain for it, this is fine. So you can use KPID is equal to KPD for most cases. Because even if we do choose the perfect root locus, this is all an approximation at the end of the day. So using 5.35 versus 5.4 or 5.5 will not really make that big of a difference on your performance. So I guess like another way of saying is if we were to evaluate it at some sigma plus j omega, actually I won't. I'll just leave it like that. Any questions? Yeah. How do we increase the accuracy? If you want the root locus to not change that much, put the zero really close to the origin. So instead of it having at 0.1, you could have it at 0.05. Then the root locus will change even less. But then the issue you deal with is that then you deal with this really long convergence. Right? You'll probably see this versus, 0.1, which is probably gonna be like this. Okay, well, that wasn't a very good example, but kind of like that instead. So then now your root locus will change more in shape, but sometimes the selling time is too long and you don't want that. You want it to converge faster. So let's say this is ZC is equal to 0.1, and this would be ZC is equal to 0.01. It's because we're limited to because on the pole zero map, we have a pole at the origin and we have a zero at minus ZC here. So we have a closed loop pole between these 2 points. So if ZC is 0.1, then we can have the fastest have a convergence of minus 0.1 t. Or this is the fastest decay rate we can have, not the or e to the negative 0.01 t if we choose ZC as equal to 0.1. More points. Okay. More like to find the gain, or are you talking about more numbers after the decimal? Oh, I'm pretty sure it's a UI thing. Maybe if I were to, sorry, online folks, I'm just gonna take a real quick look. I'm not exactly sure. I find it that you don't need it. If you choose, I think this is fine. Like just three three sig figs, I think is good enough. Or 1 point after the decimal point is enough. Yeah, because all of this is approximation. Okay, so that's a PID controller, and we're gonna move on to the lag lead controller with the last 5 minutes. Maybe I'll just go through the steps. So I have this corrected online. This is the lead compensator. So basically it's broken up into 4 steps, or I mean 2 major steps. This is the lead design, and this is the lag design. Now, because the steps for lag compensator design is actually more involved. So uh the lead design is the same. We're trying to basically evaluate the performance of the uncompensated system. Then we design a lead compensator to meet the transient response specifications. And the design includes a zero and pole location, the loop gain. So we're finding the lead gain as well. Then we want to simulate the system to make sure that all the requirements have been met and redesign the lead controller if not. Uh, Now, when we evaluate the steady state error for the lead compensated system, you have to include the lead gain because adding the lead compensator with that corresponding gain will most likely change the steady state error. So we have to then determine how much improvement is required with the lead compensated system to design our lag compensated system. So then we designed the lag compensator to yield the required steady state error, simulate this system to be sure all the requirements have been met, and redesign if the simulation requirements are not met. Um, yeah. So with this one, it is more steps because now we have to consider steady state error and how much to reduce the steady state error. So then when we choose our poles and zeros for the lag compensator, we do have to be strategic there. And we're going to design a lag compensator for the following system. This is a type 1 system, meaning that steady state error is constant for ramp input instead. So this is a type 1. So then we have ESS equal constant for a ramp input. And we want to reduce the settling time by half with 20% overshoot and reduce the steady state error by 90%. So 1/10 of the original system. We will do that on Monday. So everything up to PID controller design is fair game on the exam. I will not have lag lead compensation on the exam, but I can have lag or lead compensator on the exam as well. Uh, for midterm 2, we're going to cover basically chapters 6 through part of half of or 2/3 of 9. So up to this point. Same things, same policy as the first midterm, notes, homework solution, textbook, all are fine. You will need your calculator this time because you will need to calculate the tan or arctan. And if you get stuck or you make a mistake, I will work with your mistake. So if you have a mistake in part A, but use it for part B and C, I will work with it for parts B and C as well. So uh, I will release the last year's midterm with the solutions. Maybe this on Monday or maybe this weekend, so then you have time to look it over. And Monday there's no class because it's Veterans Day, it's a holiday, so don't come to school or come to school. I don't care, but don't come here. All right, I'll see y'all. See y'all later. Have a good weekend.
Thomas, I had a question on the homework.
Yeah, give me a sec.
Yeah.
Someone, yeah.
So like when calculating KP,
Mhm.
done is 1/CGA. So I'm
Uh,
not sure
It's gonna be 1/CG. Yeah, CGH.
yeah,
Yeah, yeah.
I'm not sure whether it's included the K or not.
You don't include the K. That's what you're trying to figure out.
Okay.
Yeah.
Got it.
So the midterms, like the grading midterms.
Yeah, it's right there. Yeah. So you have a question online now?
Yeah, for the homework for finding the magnitude of the closed loop system, do we have to do the magnitude criteria or can we just look at MATLAB like the root locus plot?
Is this for number 2 or 3?
Either of them, I guess, because
Yeah, yeah. You could just use MATLAB.
okay, cool.
Yeah. If you want to find it by hand as well, it's good. It's a good exercise, but yeah, MATLAB's fine.
Okay, cool. Thank you.
Yep.